Yeah, thanks for the introduction. So, today's talk is titled Metascheduling of HPC Jobs in Day-Ahead Electricity Markets. So, this is a brief outline of my talk. First, I'll present the introduction, which is basically a motivation of the problem statement and why the problem is relevant in the coming years. Then we'll go into the methodology. The methodology consists of three main parts. One is a Q-waiting time predictor which we developed. One is the electricity price prediction and the main metascheduling algorithm. Then I'll describe the experimental setup and give you the results. So, high performance grids which are composed of supercomputers have been very important in accelerating many scientific discoveries in the last many years. So one of the prime examples of this is the discovery of the Higgs boson. So prior to the announcement of the discovery, the millions of CPU hours of computational power was used to sift through the data from the collision. So and other examples of these large-scale grids in the US and Europe are the EXCEED project in the US and the Open Science Grid, which is in both the US and the Europe. So these grids are primarily used for a lot of simulations ranging from biological simulations, seismic networks, weather modeling, and many other topics. So of late, the cost of acquiring the hardware for these grids has become, not only for the grids but also the individual systems, has become comparable to the operational cost, say, across the lifetime of the system. For example, in Oak Ridge National Labs Titan supercomputer, the cost to build the machine was around $100 million, and the actual cost of running the system and the electricity bill paid per year is around $9 million. So if we project that the system will be around for 5 to 10 years, the electricity costs become as high as the cost of procuring the machine. So it is estimated that in general the electricity costs can go as high as 25% of the total cost of ownership of the system. So because of these high costs, there has been a lot of research in the past 5 years on how to save costs, and multiple approaches have been used for this. So one of the approaches, and this is very common, is to switch off unused nodes whenever available. So there have been approaches on how can we switch off nodes fast, how can we sleep schedule, how can I build scheduling algorithms such that I get maximum number of nodes which I can switch off, etc. Another line of work has been primarily motivated on the hardware side, where there are chips where I can change the voltage or frequency of the chip, and that will reduce the computational capability of the chip, but it will give me lesser power. So there have been works on how can I tune my workloads if I'm allowed to change the frequencies of my CPUs. And there are also a set of works which propose the use of renewable electricity in supercomputers. So these works primarily consider a supercomputer which is augmented with a renewable energy source, say a solar power generation unit, and they look at how can I schedule maximum number of jobs at times when maximum green energy is available. So a general viewpoint in the HPC community is that, so if I'm going to reduce the utilization of my system or slow down the applications, then that is not a very good solution, because HPC systems are looking for performance, and the codes are expected to scale and run with maximum performance. So some of the previous approaches may not be applicable. For example, the voltage and frequency scaling based techniques may not all that be applicable for HPC systems as they're applicable for cloud servers or other kinds of systems. But approaches like switching off unused nodes and using renewable electricity are complementary to our approach. So our proposition in this thesis is that we can reduce the operational cost in a grid by exploiting price fluctuations that exist across the locations of the grid. So these price fluctuations come from the differences in the prices in various electricity markets. So because electricity markets have been deregulated in various countries, different states in a country are governed by different electricity operators. For example, this figure shows the electricity trading zones in the US. So each zone controls the electricity prices in a particular area. For example, California ISO controls the power in the California area. So it gets to decide what are the prices, how much, who are the suppliers, etc. And each operator is independent of the other operators. So these kinds of wholesale markets are becoming popular in many countries, including India. And an overall view of these markets tells us that there are two kinds of trading methodologies that are followed. So one is called the daytime or the forward market, and the other is the real-time market. So in the forward market, what happens is that customers tell ahead of time what their requirement is. And the same goes with the suppliers. So typically in the day-ahead market, one day before the actual power is required, customers will bid saying that at a particular hour tomorrow I need a particular amount of power. And suppliers will similarly bid saying that I can supply X amount of power at a particular hour tomorrow. So a trading agency generally accepts these bids, and based on the supply and demand dynamics in the location, they decide a price for each hour of the coming day. So in contrast, real-time markets are much more faster, and the prices depend on the actual supply and demand in the market. So so the prices keep changing every 5 or 15 minutes, and based on the actual supply and demand, the prices keep fluctuating across the day. So the real-time market is much more volatile in the sense that it is much harder to predict these prices. But in the day-ahead market, what happens is that once the bids are submitted, the prices are announced for the next day at the midnight of the previous day. So our contention is that day-ahead markets are suitable for HPC sites because the load is easy to predict on HPC systems. So given the current queue state, that is, if I have lots of jobs queued today, I can say with reasonable accuracy that my systems will, maybe 80% of my cores will be occupied tomorrow. And we don't need a highly accurate load prediction. So if I can say with reasonable accuracy that a majority of my systems will be active tomorrow, I can bid for maybe a lesser amount in the market. And whatever remaining power is required, we can obtain that from the regular electricity source. So these two figures show how the prices vary in the day-ahead market. So the figure on the left is for Texas, and the figure on the right is for many other locations in the US. So each plot has the electricity price on the y-axis and the hour of day and the time on the x-axis. So typically on a daily basis, the electricity price increases, reaches a peak, and gradually falls down. And we can see this trend happening every day. But there are locations where day-ahead markets or real-time markets are not available. An example of such a location is Tennessee. So in these places, we consider the industrial electricity prices. So as you can see from this figure, at any given moment, there is a difference between prices at various locations. And I'm not sure if you can see clearly, but on day 3, Louisiana has a very high price. So we can exploit these prices in scheduling. So if I have jobs coming in at Louisiana on a particular day and the prices are really high, I can reroute them to other locations and reduce the overall cost of execution of these jobs.
But taking a very broad view of this graph, it looks like all these sites, right? So they all go through the valleys at about the same time, then go to the peaks at about the same time, right?
Yeah, within a few hours of difference. Yeah. Because of time zone differences that they have. Yeah.
But in that, right, so in that case, if all of them strictly follow the same times, right? So then we may not get.
If they are all following the same time, yeah, we won't have any difference.
But
Yeah.
you're saying that going deeper, right, there are some variations in the price fluctuations.
Yes, so that is even visible in this picture. So these two peaks they have a time difference in between them, and that makes the difference.
So here's the assumption that the job itself can be run on any of these data center, any of the
Right.
computing centers,
Right.
without much overhead in terms of the
Yes.
moving data.
Yes. Yeah.
Which potentially means that since you're different time zone, you could open this up to, let's say, European computing centers and so on.
Yeah. So we do test run. Yeah.
Okay, so
Yes.
where you can actually exploit the time zone difference even better.
Right. Yeah. So one difficulty in scheduling is that if I have an HPC workload and I queue a particular job at a particular system, then it usually waits for a variable amount of time before it starts. So if I want to know what electricity prices I will have to pay for executing a particular job, I have to know when the job is going to start, because the prices in the day-ahead market depend on time. And if I want to know when my job is going to start, I need to know how much time is it going to wait in the queue. So our first module of work is on predicting the queue waiting time. And this figure shows why queue waiting times are quite variable across systems. So this is a box plot which has the queue waiting time on the y-axis and different systems on the x-axis. So we picked up these workloads for these systems from an archive called a Parallel Workloads Archive, which contains historical workload traces for many supercomputers. So each workload will typically have the submit time, the number of cores requested for the workload, the estimated runtime, and user ID, application ID, etc. So each box shows the upper quartile and the lower quartile and the median, and these are outlier points. So what we can infer from this figure is that queue waiting times range from a few seconds to even many days, and queue waiting times don't follow the same pattern on different systems. So for example, here we can see that in DAS2 the queue waiting times are really small. So if we have to schedule workloads in a day-ahead market, we require a queue waiting time predictor because the electricity prices depend on the time. So we also require an estimate for the runtime of the job, because that is how long the job is going to run on the system, and we're going to pay electricity bills for for the entire duration of time. So in this work, we have first developed a queue waiting time predictor, a time series forecasting of the electricity prices depending on the predicted queue waiting times. And these predictions and the forecasts go into a minimum cost maximum flow scheduler, which efficiently schedules a set of jobs on the grid. So our experiments with two grids shows that we can simultaneously reduce electricity costs and improve response times for users. So this is a brief outline of the methodology. So typically in current grids, the scheduler is built such that it does not process every job at the moment of submission. So what happens is that the scheduler waits for the scheduling cycles happen every 5 or 10 minutes. And at the end of the cycle, it will collect all the jobs that are currently pending, that is, they have been submitted but not yet scheduled. And it will look at the different systems and then decide based on the scheduling algorithm where to route these jobs. So when we adopt the same approach, we collect all the jobs, we poll the system states of all the systems in the grid, and then we predict the queue waiting time of each job on each system, estimate the response time, predict the appropriate electricity prices, and then employ our maximum flow scheduler. So now I'll talk about how we predicted the queue waiting time of a job on a system. So this is very involved work, and I will just be giving a brief overview of the work and touching upon a few results. So to predict queue waiting times, our main assumption is that if similar jobs come in at similar system states, the scheduling algorithm will take probably the same action. So the state changes that will happen to the queue will be almost same if the job started out in the same system state. So they will experience similar queue waiting times. So our approach is to take a job and look at past submissions which were similar to this job. And to do this, we represent each point in a feature space using certain job features, and we employ a distance function based on our features. And this allows us to compare two jobs and select a good prediction model for this job. So we found out that we can represent jobs using two kinds of features. One is distributions and the other is summaries of these distributions. So an example to motivate that is, so if I submit a job in a certain queue and I see that there are lots of jobs submitted before me which require a large number of processors, probably half of the system size, then I can know I can reason that my job is going to wait for a long time because there are previous submissions which are very heavy in terms of their system requirements. So one of my features to represent this situation can be the histogram of the number of processors required by the currently waiting jobs. So if that histogram shows that there are a large number of jobs with large number of requests, large request sizes, I can infer from that that my queue waiting time will be high. And a way to summarize this distribution is to look at the sum of current request sizes in the queue. So similarly, we came up with distributions to model the systems, the state of the current compute nodes also. So in all, we had 6 distributions, which were the distribution of the request sizes in the queue, the distribution of estimated runtimes in the queue, the how much has each job in the queue currently waited, and we had similar distributions for the running jobs also. So if I know that running jobs have almost exhausted their estimated times, then I know that the jobs in the queue are probably going to start now. And so in some workloads, we found that it is better to use distributions, and in some workloads, it is better to use these summaries. So these differences come from the system side. So for example, in BlueJeans systems, we have restrictions on the request size that can be submitted to the system. So BlueJean P generally constrains the request sizes to be power of 2. So in these cases, the histograms will look very sparse, and it's easy to compare these histograms, and the comparisons will be meaningful. But in general Intel clusters, these histograms can really start to look very uniform, and histogram comparisons won't make any sense. In those cases, we found that it is better to use summary features. So in terms of summary features, we had around 16 features, which included job characteristics, the queue state, and the system state. And some of these features were also based on the user ID of the submitting user. So in supercomputers, there are generally policies where the system administrators restrict the user submissions based on various parameters. For example, the number of job submissions. So even in the SCRC Styron cluster, we have limits on each queue which say that a particular user can run only 4 jobs on a particular queue and have 2 running jobs of a particular size, etc. So, and various systems follow similar policies. So they may restrict the total number of core hours that a user can submit or have queued or have running, etc. So we also have these features based on the users, which can actually affect queue waiting time. So if a user has already exhausted his quota or is about to exhaust his quota on the system, then he's probably going to experience a large queue waiting time. So once we have the distributions or the features, we use these distance functions to compare 2 features. So when we have distributions, we use the chi-square distance metric. So what chi-square distance does is that it takes 2 histograms, looks at each bin, looks at the squared difference, and divides it by the sum of the bin counts. So this gives us a good intuition that, so if bin counts are, if you have the same difference in bin counts between 2 large bins, then it's probably okay. But if the 2 histograms have a large difference in a certain bin, and the bin values are also very different, then these bins are important. So it allows us to neglect certain bins. And when we use summary features, we just use the L1 distance. And we also found that it is good to give weights to these features, and we use Spearman's correlation to do that. So giving weights to features allows us to adaptively change which features are important at which part of the workload. So we found that the feature weights change very rapidly as we process the workload. So at this point, what we did is that, so we looked at the distance between a certain job and history job submissions, and then we tried to see whether we can use the characteristics of the neighborhood of this job to decide how to predict the queue waiting time. So when we looked at the distance numbers, we found 3 kinds of neighborhoods, and they are illustrated in case A, B, and C. So each of these plots has the distance of history jobs on the x-axis and the waiting time of the history job on the y-axis. And for the purpose of illustration, I have subtracted the waiting time of the target job for which I want a prediction from the waiting time of the history jobs. So ideally, I want, so the waiting time of the current job is at y-axis 0. So if I have a large number of historical job submissions which are near the point 0, then what that means is that I have many history jobs which are similar to my job. and their waiting times are similar to my job. So I can use these predictions to actually give out, I can use these jobs to give out predictions in later cases. So in general, what we found is that there are these three cases where case A is when I don't have too many history jobs which are similar to my job. So this can be because the current job submission is very different from all the past submissions, or because the current system state is very different. And in case B, what we see is that there are a large number of history job submissions which are close to y-axis 0, and these jobs have very similar waiting times. So it means that I have similar jobs and those jobs are also similar to each other. And in case C, we see that we have similar neighbors, but those jobs have very different waiting times, meaning that they might have come at different system states or they have different job attributes. So case A is very easy to detect. In case A, all we have is we have neighbors which are far away. So if I look at the top 5 or 10% of the jobs and look at their average distance, I know that I'm in case A. And
If you go back, case C,
yeah,
right, so the distances, right, so if you look at the first cluster, right, so many of them are at very close distance, 0.1,
yeah,
right, so or even 0, but still they show variation in the waiting times.
right,
Right?
right.
So this y-axis is just the difference in the waiting time?
The y-axis, so when I plot each point, I take the,
Point is what is depends on by difference.
yeah,
Right?
yeah.
So there is huge, right? So there is huge variation in the waiting time even if the distance is very small.
Right,
Okay, so that basically, right? So these jobs basically question the very concept,
yes,
the very basis
yes, they
of
do.
computing,
Yeah,
right?
yeah,
Which assumes that similar job states,
yes,
system states,
yes,
right? So these scheduled,
yeah.
right? So any guesses on why these waiting
Yeah, so these can happen because of multiple reasons. So one is machine failure. So I might have the same system state. So we are not in general aware of these machine failures and things like that in the workload. So if in the actual system a failure had happened, then the queue waiting time could have been affected by that. Or if administrators had actually done something to give higher priority to some other jobs or things like that, then this can in general happen. Yeah. So we have a study for ANL's interpret system which shows why these reasons become important and how they can mess up the predictions. So to distinguish between, so we are distinguishing between these cases so that we can pick good prediction models for our job. So to distinguish between case B and C, all we do is we use a clustering algorithm on these two sets, and if I do a clustering here, I'll probably end up with a tight cluster which has a large number of jobs. And if I do a clustering here, I'll get multiple clusters and many outliers. So we use a clustering algorithm called dbScan, which is a density-based approach to clustering, and it does not require the number of clusters. So when we run dbScan on this kind of a job, what we see is that dbScan outputs a large number of small clusters and many outlier points. However, on this set, it will output a small number of clusters with large number of points, with very few outliers. So we have a simple condition based on the number of outliers and the average cluster size. So if the number of outliers is very high compared to the average cluster size, then I'm probably in case C, not in case B. So we found that case A or C happen very infrequently. We found that across workload traces, only 5 to 15% of the jobs fall in case A or C, and most of the time we are in the good case B. So if we are in case B, what we do is we look at the near neighborhood of the job and we divide it into windows, and we remove outliers using the outliers output by dbScan, and we look at a window which gives us the smallest standard deviation, and we report the weighted average waiting time of the jobs in that particular window as the waiting time prediction. So in case of case A or C, what I do is we try to do a ridge regression, which is a linear regression with a quadratic penalty term to prevent the coefficients of the regression from blowing up. And ridge regression takes these feature vectors of each job and outputs a prediction. And
if you're saying that about 85% is going to be in case B,
yeah,
right? So will be is it equally distributed between case B and D? The rest
case B and
right? So 5 to 15% belong to case A and C.
I have only 3 cases.
Oh, sorry.
The D is just for illustration.
Okay.
Yeah,
Right. So hence about right 85% is in right. So
yeah, in case B.
if you have done a right.
So I don't know how the distribution is in case A and C. I don't know which case occurs more.
So if you are confident about the statistic, right? So across all jobs, all supercomputing
Yeah,
classes,
yeah,
right? Then right. So then this entire work can be lightweight, right? So where we just say that for every job, target job, I'm just going to look at the nearest neighbor in terms of the system state. So
right,
if defining the system state and the job state, right? So it's still equally important, right? So
right,
where you right? So where you have to define the distance.
right.
Right, so and then you just take the nearest job and then keep estimating time. Right, so which will work for say.
Yeah, I can do one nearest neighbor, but the one nearest neighbor can be a little far off. I mean, because we are dealing with large number of job submissions, and they can all there can be some quirks in the workload.
Where the distance is also small and the
Yeah,
difference is also
yeah, but even that can have outliers. So the outliers can very well be the one nearest neighbor. So it's better to look at a clump of jobs than just one job. So what happened when we did the experiments was we found that there are even close clusters which might be lying far away and things like that. And DBScan usually tells us that these are outlier points. So that allows us to get a more robust prediction. So sometimes ridge regression also outputs negative values for these waiting times because of some feature in the feature matrix. So in this case, we just default to doing k nearest neighbors. But we found that we did not have to fall back to this method most of the time. It was 1% of the jobs. So now I show 2 sample results. One is for the Argonne National Labs interpret system. This is a BlueGene P system with 1,63,000 cores. And we obtained predictions for 40,000 jobs in this system. So this figure here shows the heat map of the predictions. On the y-axis, we have the predicted waiting time, and the x-axis is the actual waiting time. So what I expect is that the heat map will have the counts for the number of jobs which have a particular value of actual waiting time with a particular value of the predicted waiting time. So this is like a 2D histogram viewed with colors for the bin counts. And the more red a bin or a point is, that means there are a large number of jobs there. So ideally, we would expect a large number of jobs to fall along the diagonal line, which means that the predicted and the actual waiting times are quite close. And we do see that happening. And we found that the bounded prediction error in this trace is 31%. And we had some metrics which tell us, is the prediction good or bad? And we found that in 70% of the cases, our predictions are actually very good. And when we looked at the remaining 30% of jobs which are bad, we found that in 90% of these cases, the reasons for the predictions being bad were not because our initial hypothesis was wrong. It was because of various other reasons like system maintenance or machine failure, or because of artificial changes in the scheduling algorithm. So we had one reason where every alternate Monday, the system administrators would bump up the scores of certain high priority jobs. So that would actually disturb the queue state, and in these cases, we cannot expect to get good predictions. So this was, I think, in the end of 2010, I guess. Oh, that's a 1-year trace.
It's a 1-year trace.
Yeah, it's a 1-year trace.
And you say the absolute error is only 15 minutes. So
Yeah.
15 minutes related to what overall wait time or overall constants? 15 minutes with respect to a 20-minute wait time, or?
No, this is the absolute error, so I don't divide it by anything.
Absolute error. But
Right.
what's the actual wait time related to this?
Actual wait time or runtime?
Wait time and
So the wait times are, I mean, in this system, from what I remember, was half a day or maximum 1 day. Yeah.
The ranges, right? So from few seconds to about a day. So
Yeah. But depending on the queues. So they have these test queues where the waiting time will be small and production queues where you can expect half a day to 1 day waiting time. Yeah.
Because when you say the absolute prediction error is only 15 minutes.
Yeah.
There's no context for it. It's just 15 minutes.
Right.
1 day wait time.
Right. Yeah.
1 minute wait.
Right. Yeah. So it's typically not, the waiting time is not in minutes. It's in many hours. Yeah. So that is the reason why system administrators have to adopt policies like tweaking the priorities and things like that. So that certain jobs go in faster. Yeah.
Is there a reason why you see two clear clusters over here? There's a small.
Yeah, we do have a reason. So this cluster is usually the debug jobs, which are very small and they go through very fast. And these are the production queue jobs. Yeah.
In essence, I would want the production queue jobs' accuracy to be higher than the debug ones.
Right. Yeah.
That seems
Right.
a bit more diffuse.
But the scheduling community actually has concerns about the debug jobs also, because they say that if you don't give a good, they don't say this exactly, but they would like to have users to maintain their sessions longer. So for jobs which users expect a small queue waiting time, if you don't schedule those jobs fast, so if I schedule a very small job, I would expect it to start very soon, and if that doesn't happen, and so there are actual studies which say that if that doesn't happen within 20 minutes or maybe half an hour, then the user is likely to quit and leave the session. So they want to design scheduling algorithms where you can keep the users engaged for longer so that they submit more jobs and user productivity increases. Yeah, but in a leadership class facility, you would ideally want the production jobs to be emphasized more. Yeah. So these are prediction results for some other systems. So CA Curie is a top 500 system somewhere in France, and DAS2 is a grid, and SDC Paragon is an old system at San Diego Supercomputing Center. So here we look at different jobs and look at their response time ranges and look at what percentage of jobs have what kind of errors. So our motivation behind charting this was that, so the day ahead market has a frequency of 1 hour, that is, prices change every hour. So I would like to know whether I can predict the waiting time of a job within a 1 hour error, so that I fall in the right electricity prediction bin. So that I get the right electricity price predictions for the job. So yeah, so here the green color shows the jobs, percentage of jobs for which I was able to obtain a prediction error of less than 1 hour. And we can see that for a lot of jobs, we can obtain these predictions which are within 1 hour. So this tells us that the queue waiting time predictor is suitable enough to be used for the subsequent meta-scheduling experiments. So to estimate the response time of a job, we require both the estimation of the queue waiting time and the runtime. So in HPC workloads, each job usually comes in with an estimated runtime. And in a grid setting, what happens is that the user submits the job and provides an estimate at his site, that is the site of origin of the job. So we follow a simple strategy to estimate it on any system. So what we do is look at the top 500 flops of both the systems, and we find how much performance can each core in each of these systems deliver. So when we take the ratio, we can use this ratio to scale the estimated runtime here to an estimated runtime on another system. So using both the queue waiting time predictor and the response time, and the runtime estimation, we can find the end time of the job. So with both of these time points, I can now invoke a electricity price prediction if that is required. So as I told you before, in the day ahead market, I know the prices up to the end of the current day. So if I know that my job is going to start and end within this time period, then I don't require any electricity price predictions. So if not, we invoke a price predictor based on seasonal autoregressive integrated moving average. So this is a standard model that is used in many time series forecasting methods, applications. So yeah, so it is seasonal because our day ahead markets exhibits a seasonality of every day. So every day there is a peak hour and the prices gradually increase and fall down. So we use the tools from the R statistical package to tune our electricity price dataset parameters and use this in our predictions. So this is one sample result for our predictions. So this is for city of Texas, and here we see on the y-axis we see the electricity prices, and the x-axis shows the time period, and the blue shows the predicted prices, and the red curve shows the actual prices. So we can see that the actual and predicted prices are quite close, and we saw that the percentage error of prediction is only about 8%. So we also looked at similar numbers for other locations, and we found that prediction errors are usually less than 15% across locations. Yeah. So once we have the response time predictions and the electricity price predictions, we compute a cost function and use it to annotate a flow network, which is later on used in which can then be optimized to get a good scheduling mapping. So this is a flow network which we use, and we have a set of nodes corresponding to the jobs, a set of nodes corresponding to systems, and a source and sink node. And each edge is annotated by two numbers. So the first number is the capacity of the edge, and the second number is the cost associated with this particular edge. So, and we add arcs from each job to a system where the job is compatible on a system. So by compatibility, we have constraints like if the number of cores requested for a job is higher than the system size itself, then this job cannot go there. So we have two components in our cost function. One is the response time component, and the other is the electricity price. And we have a linear combination of these two components. So WT allows us to vary how much is the relevance of CT, that is a response time component, compared to the electricity price component. So this allows us to minimize both response time and electricity cost at the same time. So to compute CTS, that is the CT, that is the response time component, we look at each job, predict the response time on each system. We look at the minimum and maximum and normalize the predicted response time. And to compute the electricity price, so we do an integral of the power consumption over time and multiply that by the price in each hour. So we have the power of the system multiplied by the time period of the day-ahead market, that is 1 hour, and that is multiplied by the electricity cost in a particular hour, and it is summed across all the hours of execution of the job. So similar to the response time, we again normalize it by the minimum and maximum of all the jobs. And once we have these costs, we can annotate all the edges required in our flow network. So one feature of our flow network is that we have a capacity constraint from a system to the sink node, which is a parameter called max Q. So this has been put in place so that system administrators don't want to schedule too many jobs at a particular system in a particular scheduling interval. So if one particular system turns out to be cheap, we don't want to route all our jobs to that particular system because it might get overwhelmed by too many job submissions. So to perform our simulations, we use a Python scheduler simulator, and we simulate an algorithm called easy backfill scheduler at each site in the grid. So easy backfilling is a very standard and popular scheduling algorithm in supercomputers. So overall, our simulations collectively span 58 systems in 17 countries and states, and these include around 10 electricity operators and 7 different time zones. So we picked up 2 grids, one in the US and one in the Europe. The grid in the US is called the Exceed grid, and the one in Europe is the Nadu grid. So Exceed has 8 systems and Nadu grid has 50 systems. And on Exceed our simulations test 10,000 jobs, and on Nadu grid we have around 1,20,000 jobs. So this is the configuration of Exceed, which is spread across various states in the US, and this is Nadu grid. So we use synthetic workload traces for Exceed depending on the statistics for a previous version of Exceed called TerraGrid, and standard workload models available for supercomputing traces. And for Nadu grid we obtained real workloads. And electricity prices are usually publicized by the ISO or the electricity price operator in each state or country. And one point that we glossed over is how do I compute the power consumption of a job. So there was a paper in IPDPS 2008 which says that if I look at the power consumption of high-performance LinPack, then this can be closely used to approximate the power consumption of a particular rack in a supercomputer or even the whole system. If I run LinPack on one rack, I can predict what will be the LinPack power consumption for the whole rack, for the whole system. So we just use their same methodology and say that if I have a job running on a particular number of cores, then if I know the LinPack power for the whole system, I can scale it down to obtain the power consumption. And the runtime scaling part is similar to what we talked about for estimation of the runtime across different systems. So moving on to the results, so we call our strategies as the MCMF strategy. So there has been a related work which considers electricity markets where there are two prices per day. That is, there is an on-peak price and an off-peak price. And people have proposed dynamic programming algorithms to schedule in these kind of environments. How can I move my jobs from on-peak hours to off-peak hours? So that strategy is not directly applicable in a grid setting because it works only for a particular system. And so we used a similar strategy called two price where I use MCMF, that is our flow approach, but the algorithm is aware of only two prices. And in order to demonstrate the importance of queue waiting time predictions, we use a baseline where I turn off the queue waiting time predictor and run the same flow-based scheduler. So in the overall results, I look at the average response time and the total electricity cost for different instantiations of these algorithms. And looking at Exceed, we see that MCMF achieves both average response time improvements and total electricity cost improvements over the baseline strategy. So the baseline strategy is when every job is scheduled at the site of origin. It is not moved across the grid. So MCMF improves both response time and electricity cost compared to the baseline. And it also improves electricity cost with respect to the two price strategy because MCMF is aware of fine level variations in the electricity market, which two price is not. However, we do see a 2-minute degradation in the average response time, which is fine. And we also compare MCMF and the INST strategy, which does not use the queue waiting time predictions. So we see that INST has a very large average response time compared to MCMF. And MCMF has both average response time and electricity cost better than INST. So it means that even if I just want to schedule workloads to minimize electricity price, it is important to look at the queue waiting time. So we can infer that because we used a value of W2 equal to 0% in the algorithm. So that means that MCMF actually does not care about the response time. It optimizes only the electricity price. And so does INST. But when an MCMF optimizes the electricity price will be more accurate because it was computed after computing the queue waiting time. And so MCMF knows when the job will start and end, whereas INST does not. So in Nadu grid, we see similar results. So MCMF has, again, both average response time and total electricity cost better than all the comparison strategies. So to look at the Exceed results graphically, we plotted the electricity cost and the average response time on the y and x axis. So we can see that MCMF dominates the other solutions, and at each point, so one particular point of interest is again the INST and MCMF point. So what we observed here is that when INST starts off, it gets many scheduling decisions right. That is, it is able to send jobs to various systems, and they started because the systems were empty, the electricity price predictions for INST were accurate. But as the queues get piled up, the INST predictions keep going wrong. So INST achieves electricity cost savings over many instances of MCMF because it does well sometimes, and for small jobs it does well because the small jobs probably won't wait for a long time. Yeah, so to sum up, MCMF achieves 24% reduction in average response time in Exceed and 11% in Nadu grid. For Exceed, we found that if we are ready to allow 1.7x degradation in the response time, we can get a $1 million savings per year for the whole grid. And this number is quite significant because the cost of running, for example, Argonne's current Mira system, a Blue Gene queue system, is almost $1 million per year. So in a huge grid like Exceed, it is almost as if we can obtain one system for free. So we also looked at the effect of the job size on the savings obtained. So here we classified jobs according to their number of CPU hours consumed by the job. And the plot show the cost savings on the y-axis here and the response time savings here. So in Exceed we found that most of our savings in response time and cost come from large jobs. So when I move around large jobs to sites where I have either less electricity cost or sites which are less loaded, I get good savings. For Nodoo grid, surprisingly, we found that it is the very small jobs which were large in number which contributed to the savings. So we had just 2 cents of saving per job, but it accumulated to a significant amount of savings. So this slide shows us why the algorithm and how the algorithm works. So we took 4 systems in Exceed, looked at whether they are in locations which are cheap and whether the systems are slow or fast. And we varied the relevance of response time in the cost function. So we would expect, so what we see is that as we vary the relevance of response time in the cost function, the utilization which is plotted on the y-axis changes for different systems. So for example, if I pick up 2 systems, Lone Star and Gordon, so Gordon is the faster of the 2 systems. And as I care more about response time, that is going here on the right, then Gordon's utilization increases much more than Lone Star's. So Lone Star's falls down and Gordon goes up. Similarly, if I look at Blacklight and Darter, we can see the same trend. So Darter's utilization goes up and Blacklight goes down. So overall in Exceed we saw that Gordon is one of the most heavily utilized systems, and this is because it is the fastest system in the grid and the 3rd lowest cost. So since we saw that result, we were wondering where the perspective of fairness comes in, because if one system is going to take a lot of jobs, then is it really fair to users of that system? So in a grid setting, what happens is that there are many users who submit grid jobs, and there are also users in the local system who don't submit through the grid portal. So their jobs get executed locally. They don't move around in the grid. So if a system is joining a grid, we want it to be fair to both kinds of users. So for each system, we take every job and we look at what is the response time that I observed when I moved this job across in the grid, that is when I allowed it to move in the grid, and compare it to what happened if I submitted it locally. So that is the QoS score that we define, which is a ratio of the local response time to the grid response time. So ideally, I would like the grid response time to be lesser. So for each job, we compute this fairness score and average it across for the whole system. And in Exceed, we performed 2 experiments. So in the first experiment, we allowed all the jobs to go through the grid portal. In the second experiment, we randomly picked up 50% of jobs and submitted them through the local portal. So in this figure, I have the fairness score for each system plotted on the y-axis, and I arrange the systems according to their cost on the x-axis. So the cost is basically how much cost does it take to deliver 1 CPU hour of computation at the location of the system. So if a particular place has high electricity prices, it will cost high average electricity prices, it will cost more to deliver 1 unit of computation at that place. And if the system architecture is such that it's a power consuming architecture, then it will again cost more. So the fairness scores for experiment 1 are the blue bars, and we see that small systems get good fairness scores, meaning that jobs there have good outcomes. So this happens because these small and slow systems, the jobs move to higher, cheaper and faster systems like Gordon. So Gordon is the only system where we see the fairness score is below 1, which is the baseline, where the grid and the local times are the same. So, however, this was not a big concern because we saw that the average waiting times at Gordon in the simulation setting was only about half an hour. So in experiment 2, for the grid submissions, we again see the same kind of result. So the grid submission results are the second.
Half an hour after the grid submissions.
Right, yeah. That is, the degradation is just half an hour, yeah. And yeah, so for the grid submissions in the second experiment where 50% of the jobs went through the local portal, we have the same results where small systems like Queen Bee and Mason and Blacklight have good improvements in the QoS score because jobs there migrated away to other systems. So then we looked at what happened to the local job submissions. And we found that even the local job submissions at these systems got improvements. So we can see that in Queen Bee, Mason, and Blacklight, and even, so in these three systems, the QoS scores for the local jobs is higher than 1. So this means that when other users submitted jobs to the grid, and this user was not aware of the grid submission portal, he still got improvements in response time. And this happens because the grid users and their jobs typically migrated away to other systems. So that is the end of our experiments, and then we look at some related work and see why we are different from those works. So as I mentioned in the beginning, there were many classes of works, and we picked up some representative works to showcase here. So as we said in the beginning, the approaches based on DVFS and voltage and frequency scaling are not really applicable to these kind of workloads. So Risbandi et al. Is one representative work in this direction. So that is not aware of electricity prices. It is suitable for HPC workloads, but some of these works are multi-site, but this particular one is not. Yang et al. Is the algorithm, dynamic programming algorithm for an electricity market with 2 prices. So this is not suitable for multiple sites. It is suitable for HPC workloads, and it knows 2 prices, so it is electricity price aware. Qureshi et al. Was a paper which introduced this whole area of electricity price based optimizations for data centers. So here they routed packets in Akamai's internet traffic network, and this is aware of, so this is multi-site, but it is not suitable for HPC workloads. So in Qureshi et al.'s work and in many subsequent works, there are many assumptions on the workload itself. So they assume that it does not take a lot of time to process these workloads. The workloads, if at all they are queued, have a first come first serve policy at the queuing site, etc. And the queue waiting times are not even more than 1 hour. So they always assume that their requests will be processed in the hour of submission. So these kinds of works cannot be directly used in an HPC setting. And there are also general works on how to schedule grid jobs, and these works are typically do not consider power or electricity price considerations. And similar to Qureshi et al.'s work, there is a work in Supercomputing 13 by Ren and He, which develops a framework called COCA, which is also aware of carbon neutrality and other emerging concerns. But again, these works are in general for internet workloads and not for HPC workloads. So since the operational cost of HPC grids is expected to increase super linearly over the coming years, our work is quite relevant in the coming years, because since we can optimize electricity prices and probably try to shift system operators to dynamic electricity price markets. So to conclude, we have developed a minimum cost maximum flow based scheduling algorithm, and we have shown experiments on 2 large scale currently operational grids. And for most systems in the grid, we can see that we obtain both response time and electricity cost improvements without being unfair to the grid or local users. Yeah. Thanks. Right, yeah. Even recently,
which actually
yeah.
supports variable pricing or has a very active energy market.
Right.
Everyone actually works in their favor.
Right.
So that's something.
Yeah, for example, the whole Tennessee region doesn't have a wholesale market. Yeah.
Right.
Yeah.
But Tennessee Valley, they also have a sort of large hydroelectric power supply. So
Right,
the cost
right.
of unit of power is
Yeah,
also cheap.
yeah.
So that's maybe one of the reasons they
Yeah.
don't have an active market.
Yeah. are power outages so common?
Luckily, in my house it is.
Yeah. Yeah. Yeah.
Right. So and in India, you don't need like grid prediction strategies to predict
Right,
power
you
outages.
just go to the newspaper.
Right.
Yeah.
So you just or just ask a
Yeah.
technical advance, right? So that'll give you a thing.
So it is actually possible to, I mean, if not power outage, it is possible to get far more accuracy on the power prices itself, because the loads are going to be the load prediction is a different domain, and people use many more inputs there. There is what customers do I have, how much are they going to process. It's possible to get a lot of domain data from there. So
Right.
yeah.
Load prediction thing, the smart grid perspective,
Yeah.
power grid perspective.
Yeah.
Right? So load prediction, while it's possible to do it with reasons like you said, the aggregate, doing it in a more fine grained way is a little bit more challenging. I mean, the early one
Right,
that
right,
we do
yes,
is actually,
yes.
and even sort of time of day averaging and so on,
Right.
is actually reasonable estimates.
Right.
But one of the challenges in even load prediction, which influences energy prices,
Right.
from our grid perspective,
Right.
is things like both renewables coming online, because of that
Yes.
there's going to be much more flux in the supply
Yes.
side.
Yes.
So those are that the energy markets might actually
Yes.
move much more quicker.
Yes.
And the other is the different types of variable loads that come into the form of electric vehicles. Again, I'm talking US market. Right? So things like electric vehicles and so on have much different load profiles. Electric vehicles, like
Right.
freights,
Yeah.
right?
Yeah.
And that's one of the concerns, at least in cities like Los Angeles
Yes.
and so on, where they have a lot of EVs. So you come in and plug in a
Right. Yeah.
electric car.
So, but those kind of consumers are not going to come to the wholesale market. They're going to go to the retail market.
In aggregate, they'll add up. Because at the end of the day, the power utility is going to go and purchase.
Yes.
From the
Yes.
wholesale market,
Yes. Yeah.
based on their demand.
Yes. Yeah.
What they're predicting.
Yeah. But that bidding happens on a higher level. You know?
It's a
Yeah.
course of time.
Yeah. Yeah. Yeah.
So,
Yeah.
but the renewables is a big.
So Ren and he, the work in SC13, they consider, I think, some amount of renewable sources. Yeah. Yeah. And there is also some work on how to provision VMs according to these constraints. Yeah. Yeah.
Say something more about the first flow supercomputing.
Yeah. So the network simplex algorithm is a polynomial time algorithm to find an optimal flow in the minimum cost flow network. So yeah.
What is max flow? I mean, are you saying that flow has to be above a certain value and you try to minimize the cost? Is that what you're
So yeah. So it will achieve the maximum flow. It won't constrain the value of the flow. Given that I can have multiple maximum flow possibilities, that is, I can have multiple ways in which I can route the maximum flow. It will find the particular way which gives us the minimum flow, minimum cost among these. Yeah. So it borrows a lot of ideas from the simplex algorithm and it adapts that to the network setting. So that was a paper by James Orlin from, I think, MIT maybe 2 decades ago.